Hello, good morning, everyone. So my name is Handong Li. I'm coming from Northumbria University. My topic today is a simulation of solar wind powered electric vehicle car park for reinforcement learning. So, in my presentation today, um, let me just introduce the project background. So first, let us just think, where do emissions come from? In the UK, from the report that in 2019, the road transport accounted for like 25% of the UK's CO2 emissions. And locally, in my city, Newcastle upon Tyne, these numbers become 32%. So if we can reduce the transport CO2 emissions, we can save the environment. So there is two example solutions for how can we use the renewable energies to reduce the CO2 emissions. Firstly, we can use solar powered EV charging stations, and secondly, we can also combine the wind turbine. We use the wind power and the solar power to charge the EV and also charge the batteries. We can also sell the energies to the main grid. So in my project, the systems is like this slide. So we have a solar panel, we have a wind tower. We want to use these renewable energies. We want to use that to charge our EV fleet. So if this renewable energy is bigger than the demand of the EV fleets, we can, of course, we can charge our EV fleets, but we can also save this energies into the battery. So if this renewable energy is not enough for the demand, we can also borrow some energies from the main grid. Um, but the most important thing, we need to build an algorithm to match the renewable energy generation, and also the demand of the EV fleets. Uh, so this is our background. So with this, we have to use the reinforcement learning algorithm. We have to build our environment, which is the renewable energy generation and also the EV charging. So these two parts, we can generate the data from the history data. For example, Newcastle weather data, and also some depot in Newcastle in some cities, like for example Oslo, Leicester, like this. We also need to design our reward function, state, and actions to use these three to communicate with the agent, which we will use a PPO algorithm for our reinforcement learning. So in my project, data can be from the Oslo, Leicester, and Newcastle. Imagine that in our charge stations, we have 10 charging pairs. We separate that into like one day, 24, for example, 24 hours. So we define that one unit of energy is 50 minutes for one charging pairs or vehicle energy demanded. So for example, maybe one vehicle need to charge for 45 minutes, then it needs 3 units of energy. So charging pairs number X, for example, we have three available charging slot. We need to choose one slot to charge our vehicles if the vehicle doesn't need 1 unit of energies. So the question is, if we have an EV and we need 15 minutes to charge, we have to choose one available slot out of three available slots. We need to charge these three. We just use this to match the renewable energy generation. So our choice of the time slot depends on the 3 points, which is the system constructed. So during the green feasible time period, charging the EVs to meet the demand. And also, if you charge the EV earlier, it's better than later. So thirdly, charging time has to match our renewable energy generation. So the expected results comparison is like this. The renewable energy is consumed by the original data. So we need to learn from the original data, for example, the weather data, and also the EV charging data from some depots or charging stations. Also, the allocate of the renewable energy follows a random policy. So uh, we need to design the random policy. Like for example, if we have a 10 times slot, we need to random select the one slot from the 10 out of this 10. So thirdly, under the reinforcement learning algorithm, we need to figure out how the renewable energy consumed. And finally, when the weather conditions at the next step are known, so for example, if we know what happens for next time step, so we need to figure out how the reinforcement learning assigns renewable energy solutions. We call it a God model. So we know exactly what will happen in next one day or next time step. Then we can make a decision. We can make a comparison for this reinforcement learning. So this is a case study. Now we have the data from listers. So totally is over 1,000 data of 4 vehicles from 2018 to 2019. So this is over 300 days. So we have a charging point. We have charging point. We have locations. So we have a card, which is vehicle ID. So the last clues is energy consumption. So we have the vehicle ID, we have the energy consumptions, we have the durations. Then we can figure out because the duration is a really long time. Then we have a space to figure out so which time is suitable for our algorithms to match the renewable energy generation. So after the decision from the reinforcement learning agent, so if we can use the renewable energies, so the rate has improved by 4% from the original data allocation. So here we have three policies. First is the random charging strategy, means we just random select the time to charge our vehicle. Secondly, the priority charging strategies is like just like our customer behavior. When you arrive at the charging stations, you just charge your vehicles until you reach the needed energy. Thirdly, is our reinforcement learning agent will make a decision. We call it RL charging strategies. So just want to match the reinforcement learning. Just want to match the renewable energies. Our agent will make a decision. So just make a comparison with these three strategies. So our reinforcement learning will improve by 4% from the original data allocated. Why the number here is not very dramatic, it's just 4%. Because if you learn from the original data, you can see that it has a really long time duration. For example, the first one is over 2 days, and the consumption of the energy is just 3 kilowatts per hour. So this is really small. And also, the start time is in the afternoon. So if you compare with the energy generation, you will find that if you use the priority policies is almost the same because the charging action just happened in the afternoon and almost matched the renewable energy generation. So here, with this data, the reinforcement learning cannot improve it very dramatic. So here we have a data validation with the real situations. For example, we select one day is from here is 2019. March 28th, we need to add in 2 years because we don't have the exact the same data, same dipole data at the same year. So to see what happens. So at this data, there is two vehicles they want to charge at this time. It's about 12 uh, o'clock. So they want to charge, but at that time we don't have enough renewable energies by this green line. Green line, we don't have enough energies to charge it. So if we don't take any actions, we need to borrow energies from main grid. So and then next time we need to charge the two vehicles. But with the help of the with the help of the reinforcement learning, so what we gonna do is we just separate these two vehicles. So what really happens is that at the first time, the vehicle one, it didn't charge. It just nothing. It was doing nothing there. And after just wait for next time when the renewable energy is enough, it just move to next time slot and then charge, and then it start to charge. So because you can stay here for quite a long time compared with our original data, you can stay here for quite a long time. So it doesn't matter if you want to charge at this time or next time. So with this, it can save energies. So this is the algorithm tells you if you're doing this, you can just save the energies. You don't need to borrow energies from the main grid. So this is our result here. So you can also log on to this website to get more information. This is our research team, Northumbria University. So also, if you want to have more questions like technical details, you can don't hesitate to send me email to ask for like algorithms, code, and all the details about this project. And thank you for your listening. This is my presentation.